Welcome to the New Electromagnetism Advanced Model of Magnets. This is the 11th video of the New Electromagnetism video series, and New Electromagnetism is the fourth book of ethereal mechanics. This is being presented to Patreon members on 25 August 2024, and it will be made public in a premiere on 19 September 2024. Patreon members usually get at least 4 weeks advanced view of everything, sometimes up to a couple years. Okay, so what we're going to do in this video is we're going to give a brief overview to set the context. Where does this fit within the new electromagnetism galaxy? And where did it come from, what its original roots are, and how it's evolved to what we have today. Then we're going to get into what is a magnet. And then we're going to show you the EM04 advanced models of that magnet. And then we're going to show you a Physics 2 software considerations. And we're going to demonstrate some experimental data. So the EM04 model of magnets is the most precise model of magnets to date. Okay, there was some earlier video releases, probably about 15 years ago in the New Electromagnetism V3 series, and those video numbers are D002 and D003. Okay, we're more precise now because we have now included Coriolis and halo effects. Okay, and the EM04 methods were actually developed in the late 2000s, and they were published in the New Magnetism paper NM-PDF, which you can find at this location here. Okay, in fairness though, Maxwell did come up with the edge current idea of magnets. He called it the method of shells. But unfortunately, he just had a brief description of it, didn't really do any reduction to practice, and it has been forgotten. Nobody picked it up from Maxwell's original work. It was something that got completely overlooked. And up until 2007, I thought, well, I was the first person to come up with this idea. Okay, but I am the person that is bringing this idea into the front and giving it the precision it needs that far eclipses anything Maxwell published in his books. Because they do not consider Coriolis effects, halo effects, or anything else in any other model anywhere else. Okay, so what is a magnet? Now, first you have to forget everything you learned. Okay, we do not use a flux model for EM04 because our model of magnetism is too complex to represent with a simple vector flux model. We actually have a matrix field that's too complicated. Second of all, this model, which dates back to, I don't know, the late 1800s, is ridiculous because here they show that the major effects are coming from the ends of the magnet, which isn't in fact the case. And I'll show you using MagnaView film that where the north and south meet, that's where all the power in the magnet is. Not at the ends like they show here. Secondly, okay, you can see the density of the flux lines. The filings are much more here, and they're very sparse over here. And actually, this is what we would call halo effects. But, excuse me. And the worst part about this model is that iron filings affect the field. So you can't trust this as a representation of a magnetic field because each of these little bits of iron are going to distort the field. And why physicists are using this, I have no idea. And this is why you get all this nonsense about magnetic monopoles, because this looks like a dipole. It is so ridiculous, the stuff that's out there. It really is. Okay, but the old flux line model is still useful. However, it's not complete, and it can be more confusing to use. Okay, it's useful, but it's not complete. Understand that. We're going to show you effects that the flux line model can't. But for some applications, you might want to still use it. That's fine. Just understand its limitations. Okay, but with the New Electromagnetism V5 direct line of sight solutions, line of sight, also known as optical solutions, we can show you very simple ways of modeling how magnets and interact without having to use the right-hand rule and say the flux is this here, then employ the right-hand rule at this point in space where there are these iron filings. Instead, you'll see it's a simple line of sight operation. It is so easy, even a physicist can do it. Okay, so to begin, we have to discuss what magnets are. Let's start at the beginning. Magnets are constructed from a special type of paramagnetic material that can remember. And these special variations of paramagnetic materials that can remember are called ferromagnetic materials. Okay, the name ferro means iron. So this is the magnetism of iron. Iron was the very first material that we knew that could be magnetized. That's why everything starts from ferromagnetic. Because there's other materials that are not made of iron that are also called ferromagnetic. You have nickel and cobalt and some other, this thing goes on. There's a whole bunch of other ones. Okay, and so basically what we're saying is this iron was the first one that we understood to be magnetic, that we called a magnet. And later on, as we learn more, we found other things that express the same properties like iron did. So we call all of these ferromagnetic materials, because iron was the first one. Just like in Navy, the first ship of its class is the name of the class, and that's kind of the same idea here. Okay, but there's also paramagnetic materials, and the difference between paramagnetic materials and ferromagnetic materials is that paramagnetic materials forget. They can't remember. And I'll explain what we mean by that in a moment. Now, you mix iron with other things like ammonium, alum, whatever, and it will be able to forget. And again, I'll explain what that means in a moment. So let's begin with paramagnetic material. Let's start with sodium. This is an atom of sodium, and what we're more concerned with is this outer electron shell. Okay, so what we can do is basically we're gonna lump the rest of the atom into this red ball here, and we're gonna display this orbital outer shell as a current ring right here. But instead of carrying around all these 3D balls, what I'm gonna do instead is just show the orbital, and the black arrow represents the normal or the direction of this orbital, and the red arrow is the normal state of that orbital. So when the black arrow aligns with the red arrow, that is the normal state of the orbital in the atom when there's no external forces applied to the orbital. So that's the normal unmagnetized state. Okay. So if we take a big blob of paramagnetic material or ferromagnetic material, because they're pretty much the same when they're unmagnetized, is their orbitals, their normal states of their orbitals are all in different directions. They're not coherent. They're not doing anything the same. And because of that, there's no net magnetic field of this material. And then what we do is we get a big ring of current with massive amounts of current in it. Okay, and what happens is, using new electromagnetism, okay, in new electromagnetism, like moving charges attract. So of every orbital, the currents moving in this direction are going to be pulled toward this guy. The ones moving to the right are going to be attracted to this guy. The ones moving down are going to be attracted to this guy. And so all of these orbitals are going to align to the magnetizing force, the applied magnetic field. Okay, using that simple rule that like moving currents attract. So now we say that this material is now magnetized. Okay, now the difference is what happens when you remove the magnetization force. Okay, for paramagnetic materials, all the orbitals return to their normal state and material loses its magnetism. It forgets. For ferromagnetic materials, the orbitals stick, well, most of them anyway, and therefore they remember their magnetization state. Okay, and they essentially become a permanent magnet. A permanent magnet. Okay. So now, the reason why we've used the term remember and forget is because this ability for ferromagnetic materials to remember is actually used in memories. And back in the 1950s to 1975, core memories were developed out of little tiny ferrous beads. These are actually very, very tiny. This is a big blow up. These are called core memories. Okay, and over 100 years ago, we applied ferromagnetic material to plastic tape to make reel-to-reel recording tape, and then we made cassette recording tape, and then we made VHS recording tape, and then we made floppy disks and hard drives, all from the same ability for ferromagnetic materials to remember. So we're using these materials to remember our data. And there's also ferroelectrogram is kind of the new thing going around now that has capabilities better than anything we've seen before as far as hundreds of years of data retention. Okay, now for completeness, I'm going to describe some of the other materials that are out there. There's diamagnetic materials and antiferromagnetic materials. Both of these work the opposite of their counterparts. For example, the diamagnetic material, their orbits are line opposite, and antiferromagnetic materials' orbits align opposite to the applied magnetizing force. Diamagnetic materials forget when the magnetizing force is removed, whereas antiferromagnetic materials remember when the magnetizing force is removed. These are some examples. I purchased a whole bunch of bismuth. We're going to do a lot of experiments on that in the future to learn more how to simulate a diamagnetic material. Okay, so the remainder of the presentation is going to focus on permanent magnets. Okay, there will be an EM04 supplemental paper and video series demonstrating how to model all these materials with new electromagnetism V5. Now it's going to be about 2 years out because there's a lot of stuff in the pipeline right now. And we're going to show you that it's going to be much simpler than the classical approach. And there will be experiments, most of which you'll probably be able to do at home. Okay, so let's get back to the basic representation of a magnet. Like I described before, a magnet is a whole bunch of orbitals where the orbitals are all aligned into the same magnetic state. Now, one thing you'll find is interesting here is that throughout the body of the magnet, wherever these guys touch, you'll see equal and opposite arrows. And because of that, we can absolutely ignore the bulk of the magnet. And the only thing we really have to worry about is the currents at the edge of the magnet. And in new electromagnetism, we call these the edge currents. And using just the edge currents, we have fantastic simulation results of magnets. Okay, now, if you have a magnet with a hole, well, then you just remove that material, and then wherever you have equal and opposite arrows, you remove them. And so what you see is you still have your edge current, but you also have an edge current on your hole, the inside, and it's counter-rotating. It's going in the opposite direction. And I'm going to show you proof that that's indeed how magnets work with a simple demonstration that a school kid can do. Okay, but let's get into some simplified nomenclature. Like we said before, like moving currents attract, and we represent that with a green barbell showing that these two are in attraction. Dislike moving currents repel, and we represent that with a red arrow showing that they get pushed apart. Okay, so if we have two magnets, or these could be two orbitals inside a magnet, it doesn't really matter. When their magnetizing state is in the same direction at the edges here, their currents are going in opposite directions, and therefore there's repulsion between these two items. Here, the currents at the edges are going in the same direction, and therefore there's attraction. Here, the edge currents are going the same because there's a lot of current lined up with each other. There's a lot more attraction between these. And that's why you'll see that when you put two magnets of the same size together, their edges are going to line up beautifully tight. And obviously when you have magnets with their direction of orbit going in opposite directions, there's going to be massive repulsion. So you see, we're not talking about field lines repulsing like they do in classical theory. And that's the way people try to explain it. It's really ridiculous. These are currents that are creating fields that attract or repel the currents of some other thing made of current. It's as simple as that. Line of sight. You don't have to worry about what the field is over here. You just say, I got a little bit of current over here, and how is it going to affect that little bit of current over there? That's all laid out in the new electromagnetism models very optically. And because it's optically, there's simple solutions to all of this. So now what we're going to do is we're going to take our model of the magnet, we're going to cut it through the middle, and we're going to look at this cross-section. If we look at the cross-section, remember there's all these orbitals, and we only showed you one-dimensional. Now we're going to show it in three-dimensional. There's a whole bunch of them going all the way from the top of the magnet to the bottom of the magnet. Okay, and as you get toward the edges, they start nosing in, and they start attracting each other. And so what you have is you have a whole crap load of orbitals all lining up, creating a huge, massive edge current. And this is why the edge currents are modeled at the center of the side of the magnet. Now, because these orbitals are pulled down, their edge currents are going in the opposite direction. So what you have at the corners up here is you have counter-rotating currents that we call halo currents. These halo currents are orders of magnitude smaller, but we'll show you a simple demonstration of where their effects are actually seen. Okay, but more about halo effects before we show you the demonstration. Halo effects are more pronounced with thicker magnets, and they're more pronounced with sharper corners. Okay, their effects diminish with nicked or rough corners. Okay, and the halo effects are present in all magnets, in all images, and I'll explain that later. But remember, they are orders of magnitude smaller than the edge currents, and for most things can be ignored. Okay, this is the new MagnaView film, and it's against the edge of a rectangular magnet. Magnet is sitting on its side. Okay, this would be the north side up on the top, south side on the bottom, and where the north and south meet, you see this massive, massive current. Now, for this film, the color is the magnitude, not the direction. Okay, you can see that there's a yellow is one of the brighter than green. And so we have this little halo effect up here. Now let me explain to you, we also have this glow here. Let me explain to you how this is demonstrated. So if we take this MagnaView film and we show it up against the side, we're looking now through the cross section of the magnet now. And this is the MagnaView film up on the side. So what you get is you get this yellow is a very, 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 very powerful color. And that's where all of these guys line up. As you get toward the edge, you get a little bit of the halo effect, but more importantly, you get the effect of this edge current on this side, which again is orders of magnitude more powerful than the halo current. And it is the reason why you get this glow up here. This is like, if you go back up here, you're looking at like a light bar on the back that's obscured by this edge of the magnet, and it's basically giving you a little bit of glow here. And again, green is much lower amplitude than yellow. And so you're seeing the glow from the other side of the magnet being projected on this side of the magnet. Okay, in the top view, now this thing there's a little bit of a misalignment here because this MagnaView film is arced. It's not sitting flat on the magnet, so that's a little bit of an error. I should have pushed it flat when I took the picture. Okay, so that's why you see it's a little bigger up here. Anyhow, so now what you're seeing here, this is probably the afterglow of the edge current. And the reason why I know there's a halo current here, and I'll have a physical demonstration of it for you in a minute, is see how this goes to almost black here? So this is the afterglow from the edge currents being projected along the center of the MagnaView film. Okay, and here it goes to almost black. And because here, right along here, almost near the edge, the halo and the edge currents cancel. And that's why we see a dark color here. Now, I have more advanced models of this MagnaView film that we're going to discuss when we get to more advanced experiments. But I'll show you why this area is dark here and why this area is green out here. This green, little hint, is a case where it's not under enough magnetizing force to affect the film. And so all of the particles in the film are in their random states, which is this kind of yucky sludge green. So we'll get more into, there's other reasons that cause this material to go black other than the forces canceling. We'll get into that in another video later. Okay, let's get to the demo video now. All right, this is the demonstration for the new electromagnetism version 5 model of magnets. Now, every experimenter must have an ammo box full of all kinds of magnets and 40-year-old pieces of MagnaView film. Okay, we're going to take a few pieces out of here right now. Let's get the MagnaView film off and see what else we got inside of here. Now, I have tons of large-scale neodymium magnets, but I have a sampling of all of them in here. So what we want, we're going to not use some neodymium. All right, we're going to start with a square magnet. You might hear some meowing in the background. That's because my supervisor, Mr. Phillip, thinks it's near his sacrifice time, and he's complaining that he wants his sacrifice. So we're going to ignore him for the moment. We're starting off with well, it's not a bar magnet. It's a flat rectangular magnet. Okay, first I'm going to show you the old film. Now, this current you're seeing here is not the edge current. This ring you're seeing is not the halo current we talked about. What this is, if you rotate it very carefully, it's basically a referred image of the edge current. And you can see the edge current there brighter than anything else. This is the most powerful point of a magnet. Okay, and let me prove that to you with a steel ball. I'm going to put a steel ball, it's going to go there, and I can't shake it off too easily. I put the steel ball here. It's not going to go in the center where everybody else says the ball is going to go. It's going to go toward the ends, either the ends. But this is kind of weak because I can still move it around, and if I just keep moving it, eventually it's going to, okay, it can't go beyond the end. We're going to discuss why it doesn't want to go beyond the end. But basically it's not strong. I can move it around. Whereas here, I can move it this way, okay, but I can't move it this way. So that means that's very, very strong. That's the strongest point of attraction on the magnet is the edge current. Now let me show you the new, let me show you the small steel ball. It gets closer to the edge. Now you have to be careful because if your corners are dinged up like this side of the magnet, dented and dinged up, when you put it here, it's going to go around the edge. Okay, you need unbroken square corners to see the halo effect. This side of the magnet is in good shape. When I drop the ball, you see it goes near to the edge, but it doesn't go over the edge. And that's a little bit stronger because the ball is smaller. But now if I put the ball on this side, okay, it ends up halfway between the edge current and the halo current. Okay, so size matters. And we're going to demonstrate this, maybe not in this video, but in a later video, using a method of image, why a big ball and a small ball have a different effect. Now, if I take an edged item, like a blade, take a rusty old blade like this, and guess what? It will not go toward the edge current. It'll avoid the edge current like the plague, but that's the most powerful point of repulsion. And again, that has to do with the shape of the metal, not the fact that the magnet is stronger somewhere else. It is being repelled by the edge current very powerfully. Okay, so the shape and size matters, and that we will explain all of that when we have the final video on the method of images, how to look at that. Now let me show you this magnet using the new MagnaView film. And again, okay, this is not the halo. This is a reflection of the edge current, or I don't know how to say it. It is a, if I rotate slowly, you can see that that yellow is the edge current, the strongest point of the magnet. Now this isn't the halo here. The halo is too small to be seen. What you're seeing here is a projection from the edge current on the back side of the magnet. I'll show you that. I think I should have already shown you that. Okay, now one thing you have to be careful about is these things are nonsense. This is saying that yellow is the weakest and blue is the most intense, and that is not the case. Okay, because look, as we get farther away from the magnet, we go from green to blue. Farther away you get, things should diminish. So they got these numbers are all wonked up here. These are not correct. Now the other problem in using these MagnaView film is that this guy cannot see sheet currents, and I'll explain what those are in a minute, where this guy can, and this guy is actually a little bit more sensitive, even though it does not have the dynamic range that this stuff does. So you kind of need both of these in order to get the full understanding of magnets. I'm going to show you something else. I'm going to show you how we can display the halo current. Now, unfortunately, these magnets are very, 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 very weak. Okay, these are like little toy magnets. I think no, that's good enough. All right, now, if I put this here on these magnets, Let me show one first. Okay, this magnet is showing these little currents on the edge. These are halos. The reason why is there is a big sheet current in the middle of the magnet, but unfortunately this stuff is blind to the sheet current. And let me show you, because this stuff is not blind to the sheet current. See that big bright spot in the middle? That's a sheet current. That is the main edge current. And the problem with it, when current is distributed over a wide area, a lot of things become blind to it, including balls. Okay, so when you have a wide current distributed over a wide area, it's less attractive than if it is concentrated into a very, very tight current. And that is why a bar magnet looks like the more powerful ends are at the ends, because of the nature of a sheet current. But all the power is actually emanating from the center. And I'm going to show you that the halo currents at the end are going the opposite direction as the sheet current, or what we would call the edge current. It's just spread over a wider area. And we're going to show you that they're backwards. Now what I'm going to do is I'm going to gang up these guys. Okay. Now what I'm doing here by doing this is I'm concentrating the halo currents. Let me show you what I mean. So if I put this guy, let me turn it on. It's so that the little letters don't interfere with the sheet. Now look at this. Can you see that? I'm going to zoom in. These little edge currents in here, are the halo currents, are now concentrated and they're displaying yellow. So effectively we've doubled the current and we have concentrated the current, not the sheet current, but the halo currents in between the magnets, to show you that these are now more powerful than the edge currents here. The problem with these is they're buried in the sheet currents, which aren't going to help. So a ball is not going to quite be attracted to these, I don't think. Oh, it's hard with this thing is wonky. Nah, I can't keep the ball there. The ball stay there, yes. Okay, so these, if you notice also, let me zoom in on it so I can show you better what I'm trying to say. Okay, notice that the halo current's got a lot of clear space around it. This little concentrated edge current, okay, it's got a little tiny dark space around it, but then there's other currents next to it. So unfortunately what's happened is, even though we've concentrated the halo current, the sheet current we've also concentrated. So we almost have equal and opposite currents right next to each other. So that's why a very weak point of attraction. But let me prove to you that there is a different direction of current in the center of the magnet than there is at the edge. And we're going to use these concentrated edge currents. We've got two of them to demonstrate this to you. So what I'm going to do is I'm going to turn this vertical, okay, like that, and make sure you line these things up perfectly. Any little misalignment really whacks up the effect you get. Now let me take this guy. Remember, this guy has got a little edge current drawn into it, and I'm going to bring this real close. And depending on which side we are, we're going to be attracting. So now we're attracting to the concentrated halo current. Now let me draw it toward me, and you can see as we get into the sheet current that's there, it's going to repel. I'm going to pull on the string very carefully. Okay, and you see it starting to repel. Okay, so there is a current in the middle here. Okay, and you can see the repulsion. It doesn't want to attract, but if I go to the concentrated halo current, it attracts there, which shows you that there's contra-rotating currents in this magnet. Let's use a ring magnet. Now a ring magnet has an edge current on the outside and an edge current in the ring, like was demonstrated, and we can see that with the MagnaView film. There are other kinds of magnets out there. There are magnets where it's not on the edge. In this case here, this is what we call a fridge magnet. This is designed because the things are attracted to the edge currents. Then you want something with as much edge currents to stick to something like a refrigerator. And so these are optimized because you have more current passing through. And again, these are counter-rotating currents here. Okay, and then now this is a little bit different. Now, when I put the ball there, it'll stick to an edge current, but you can also make it stick in the middle. And then you can make it stick on the edge current. And then a green current. The MagnaView film might be interfering with it a little bit. So let me just go using the marking. So there, it sticks on the middle current. Now this is a strong point because I can shake it and it won't move. And let me put it on the null point between the currents. It's there now. And I can shake this. This is very stable. It doesn't move. Well, because I dropped it and you had the mechanical hit of the flow hitting the, again. If I don't drop it and disturb it, it'll stay. Okay, so you got to use your MagnaView film to know where the currents are. Now, let's show you the counter-rotating currents. Go back to our ring magnet. Okay, now this is a calibrated magnet. It has a little arrow showing the direction of the edge current around the outside. This is such that if you roll your hand in the direction of the edge current, your thumb will point north. Hold on. Okay, so you see it's stuck right to the edge. Edge current to edge current. Okay, because the current is going this way, that means the edge current on this magnet is also going this way. So I'm going to use a marker. Let me get this out of the way to draw the edge currents. Now I'm not drawing it down here, I'm drawing up top so you can see the direction of the edge currents. The actual edge currents are right here. Okay, so let's get a little tiny magnet now. Tiny little magnet. And this little magnet, I have put tape, blue tape, on the north side. So I'm going to put it on the edge, and you can see it aligns with the north side because north side up means the edge current of the little magnet is spinning in this direction, which aligns with the edge current because like moving currents attract. Now let me put it on the inside. And it's like, oh, it's still north side up. You say, oh, you lied to me. No, do the right hand rule. Okay, right hand rule means that this side of the magnet in here is the currents are rotating in this direction. So that means the currents have to be rotating in this direction. Counter rotating. Now you notice the direction is different than the currents on the outside. These currents are rotating in this direction. I'm sorry, these currents are rotating in this direction. These currents are rotating in the opposite direction. Okay, so that shows you that a magnet with a hole in it has counter-rotating currents. Again, though, make sure that's the kind of magnet you have and that you don't have, you know, one of these screwy things, these refrigerator magnets. That's why the MagnaView film is immeasurably valuable. All right, now let me prove to you, because I can't get this little magnet to stick to the edge current, to the halo currents, because the halo currents are way too small. So what we're going to do instead is, okay, let me go back to demonstrating that if I release a ball, it's going to get stuck at the edge. All right, so what we're going to do is we're going to get rid of the halo current. And the way we're going to do that is we're going to get a stack of playing cards that are exactly equal to half the thickness of a magnet. Okay. And we're going to put this magnet up on its edge. And then we're going to get a piece of wood with some more playing cards that bring the surface of the wood even with the... And then this here is now our edge. So now we have a setup here where we have an edge current exactly as we would see at the top of a magnet, this being the top of our special magnet now that does not have a halo current. There's no halo current. It goes over the edge. Of course, it's going to roll over the edge and go attracting to the magnet. Okay, so it wasn't blocked by the edge because there's no halo current here. Let me do that again. Okay, again, it wasn't blocked at the edge because there's no halo current there to block it. Of course, it went over the edge and got attracted to the magnet. That's just normal. Okay, that is the demonstration of magnets for the new electromagnetism V5. Thank you. Okay, so you saw how the BB behaved, and BB is an acronym for ball bearing. Okay, so in order to explain that, I got to teach you some of the method of images for magnetism. This is going to be a small subset of the method of images just to explain how the BB works. Now, most of the slides were taken from the D002 and D003 from new electromagnetism from 10 years ago, and the slides have been improved with the new halo effects. Okay, so in the magnetic method of images, if you have a magnetic body that I'm showing here as a cat, and you have it up against a piece of paramagnetic material or ferromagnetic material, the image of that magnet is going to be reflected from that material. And what this does, and this is also called the first order method of images, because first order represents current objects with current flowing, which are magnets. Second order would be time-changing currents. We demonstrated that in the previous video, video number 10. So let's see this effect. So if I take a magnet and I suspend it over a sheet of paramagnetic material, let's say soft iron, this magnet is going to be under the effect of an image of itself that is equally far away. So if this is from the surface of the paramagnetic material is D, it will see an image that's D that farther away. And it'll be a positive image of itself. So it will be attracted to its image. Okay, and all you have to do for all the modeling is use the fragmentary model of the edge current against another like magnet twice the distance away, compute the attractive force between it, and because this material is not perfectly reflective, you multiply that by a factor, we're going to say 80%. We are going to have another video where we're going to measure all of these factors. I think we can derive them from the relative permeabilities and all that stuff. I think we can do that. I don't know yet. We're just going to do the measurements first to get the factors, and then we're going to see if we can correlate them to the measured permeabilities. Okay, and then you get very accurate results doing this, and then you can compute the attraction between a magnet and a sheet of steel doing this. Now, the interesting thing, which nobody else talks about, and we're the only people that do, is, well, what does something on the other side of the sheet see? Well, if 80% of the image is being reflected back, that means 20% or a reduction of 80% of the force can be seen from the other side at a distance equal. Okay, now I'm showing this offset a little bit, but it would be at the location. So an object on this side would see that image where this magnet is, but reduced by 80%. Still have to work out some of the details of this because the thickness is going to affect that and other things like that. So that this part here, I have done some measurements with an ammo can using that as the magnetic barrier, and it works pretty good. But as things get thicker and with different types of materials and anti-magnetic materials or whatever, it's going to be a lot different. We have a lot of work to do in this to categorize and characterize and measure all these materials to get a general sense. But essentially, this is reverse images. Again, because new electromagnetism can be reduced to optical solutions, we can do optical solutions for all those materials we discussed in the beginning of the video. Yep, I just talked about that. Okay, now for other shapes, let's say we have a steel ball. Okay, when you put it close to a magnet, you're going to see a reflection, the image of that magnet in there, including I'm showing the halo current. And that's how you would compute the attraction between, let's say, a magnet and a steel ball. Don't have these models worked out perfectly right now, but I'm going to show you a little demonstration, or we showed you a demonstration using a ball bearing. We showed you a demonstration using ball bearings in the demonstration video. And now we're going to use this image, even though we don't have all the stuff worked out, to show you why the ball bearing stops near the edge. Okay, so if you release a ball bearing on top of we're using a circular magnet here. Okay, there's going to be an image induced of the edge current in that magnet. Right now, we're not considering the halo current because the halo current is orders of magnitude smaller and it's very far away. So the number one attraction to this ball bearing is going to be the edge current. Now, as the ball bearing moves toward the edge, the major force here, this is starting to go vertical, perpendicular to the surface. And so the ability for this edge current to pull along the edge is becoming perpendicular to the pulling vector. Okay, I think people that understand physics see why, as it gets closer to the edge, the pulling force is going to zero. But what's happening, because we have an image of the, what do you call it, the edge current in the magnetized material, that edge current is now resisting against the halo current. And there's going to be a point here where these get very close together, such that this force of repulsion from the halo current is going to override whatever component of force is remaining here, and this ball is going to very stably stop before the edge. Okay, now for the ball on the refrigerator magnet, this is the conceptual. When you place it over the line, you basically get an image of the current in the ball, and the ball is attracting to the current. Over here, you get images of the current in opposite directions, but because these currents can be continuous, it actually makes an image that is bent. And so what happens is this ball gets stuck in the middle, because if this ball moves to the right, this component vector goes normal. And as it becomes more normal, the ability for it to pull the ball diminishes, where this guy tends to become more flat and its ability to pull the ball increases. And so there's a steady state position halfway between the lines where this ball wants to be. And that's why you get stable states on the line or directly between the lines. Now, granted, these lines aren't perfectly straight, so you're going to have some variations in where the ball wants to sit, depending how well they magnetize these refrigerator magnets. Edged blade wants to stick in the middle. It does not want to go on the edge current. It wants to be in the middle. And I've come up with a method of images to explain it. I'm not really happy with this one right now. I think there's something else we have to look into. That's going to be part of the research for the full method of images video. This is what I got now. I'm not going to explain it because I'm not really happy with it, but it's not bad. It explains why it wants to be in the middle, but it doesn't explain why it doesn't want to be on the edge current. That's the part I really haven't figured out here. Okay, so this is the release schedule. I've had to push the paper out for Patreon members to Sunday, 1 September, because this video for model of magnets just became way too long, and we were only halfway through the video. Okay, and I still might not be able to get this Hall effect video out tonight either. So things are going to slip. They always slip. There's just so much work to do. This is the updated punch list. I'm not going to discuss it. Just got it in here for this is the current state of it right now. Let's get into modeling of magnets. Now we have a model of magnets. Let's show how we model that model of magnets. Okay, so it should be plain from what I've demonstrated that the edge current and the halo current are pretty much all you need. But the halo current is so small that you pretty much can ignore it for just about everything except for close-in measurements like we demonstrated with the ball bearings. And in fact, so what we do in the physics software, you can see you can turn on the edge currents here. We actually represent the edge currents as a filamentary conductor using the exact same model that we use when we look at copper wires. No need to reinvent the wheel. But for most purposes, we turn this off so it's not visible. But you can see it's right where the north and the south meet. That's where the edge current is. And that's where all the ball bearings want to go. They want to go toward that massive edge current, unless, of course, they're stopped by the halo current. We don't presently have the halo effect in the Physics 2 software. I may add that at a future time, but it does not really affect our experiments. And this is one of our experiments. I gotta see if these experimental videos are released. But anyway, these magnets are spinning around this axis here, and we have a oscilloscope hooked up to this copper D here. And let me explain this video for you. The blue is the Coriolis inertial force of the magnets because they're spinning, and therefore the currents induce the Coriolis current effect. Here is the magnetic effect, magnetic force model effect. When we add those two together, we get the black trace, which is the sum of all the new electromagnetism effects. And the red here is the measured from the oscilloscope for the experiment. Yes, we did real experiments. This little anomaly is something that's on my list of little anomalies to explain. In this experimental set, there's 54 different variations. Because you saw from the film that the halo and edge currents are very tight very, very filamentary. We just use a filamentary model of new electromagnetism V5. Okay, so if we take all the consolidated equations of new electromagnetism V5, we can use the fragmentary forms. Now, the induction inertial effects are not expressed by magnets because there's no time-changing current in a magnet, unless, of course, you break the magnet. In that case, you may have to do this. Okay, the Venturi inertial forces are not expressed because there is no current speed up due to current squeezing together. All you have is a bunch of orbitals. Everything's traveling at the same speed all the time. There's no acceleration. Now, centripetal effects are there, but they are too small to be bothered with. Now, I'm going to demonstrate that for you in the next video. So if we take a magnet, okay, every little circulating orbit here has a centripetal effect, which would affect a charge out here. But from the other side of the loop, now we have the equal and opposite effect. Okay, so these would combine at a target charge. But at benchtop scale, this might be a centimeter away or less, doesn't really matter. Whereas the difference in distance between this side of the loop and this side of the loop is measured in nanometers. Okay, so if we take a nanometer and we divide it by a centimeter, we end up with that the difference between these two forces is too small that we couldn't even measure the difference, the effect of these orbitals on this other charge. Okay, and this is good for electrical engineers because benchtop and larger experiments can totally ignore this effect. However, if you have researchers working at the atomic scale, they're definitely going to have to take this effect because as this gets closer and closer and closer to the orbit, this effect becomes significant. Okay, just keep that in mind. It's too small for us to deal with for most electrical engineering applications, so we're going to ignore it. Okay, again, you can work out all the complex geometries by yourself, but the Physics 2 software, we don't have edge effects yet. We're going to have that in the future. And for any of the method of images, all you do is create a parallel image of your item and then multiply by a factor to get the true force. As a matter of fact, that's how we're going to develop the effects of all the materials when we do all that material testing later. Okay, conclusion. I've shown you a more advanced model of magnets that yields very precise results. Okay, a model of magnets you're not going to find anywhere else because I've demonstrated edge currents and halo effects. I've introduced a method of images for modeling magnets with other types of materials. And in the previous video, we did the induction effects, which we call the second order method of images. Okay, demonstrated a more proper interpretation of the magnetic viewing film. A more complete interpretation along with computer simulated film is in the works. Because in order to be sure that we got it right, we have to simulate it to make sure our models are correct, that we get the same colors as the film. Okay, that's just to be absolutely sure that we have the model down perfect. We got to simulate to get the same colors. Okay, but you will not find this stuff anywhere else. No textbook. If there are other people expressing this stuff, it's because they've been plagiarizing me. Okay, this is the Ethereal Mechanics YouTube site. You can get there by either going to Ethereal Mechanics on YouTube or I believe this.com will get you there. Okay, all of the videos are premiered on Thursday nights at 9 p.m. We basically took the spot that the Y-Files were using because they're not using it anymore. Okay, and all of the items for each of the different things are in their own playlist. Once we're done with new electromagnetism V5, we'll update the playlist to put everything in order. Okay, and then we will put all the videos in order on the main, so you don't have to go through YouTube to find them. You can go in here, you can click on the paper, you can click on the videos, you can click on all the supplements. This is not up to date yet. This will be done. After we're done with the last video, we'll update this website. Okay, this is the blog site. This is etherealmechanics.info. Great shout out to Sebastian for hosting this. If I can get to the point where I don't have to do my JOB, I can put killer time into Ethereal Mechanics. Right now, my JOB is the #1 funding for this effort. So if you want to come to the Patreon site and help us out, and $5 a month, if I can get enough people to give me $5 a month or more, because software will be available to the engineer, the Physics 2 will be available to engineers and above. And we have voting privileges, and I'm going to give more items to these guys in the future once I get some more time, more ability to contact blah, 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 blah. But thank everybody for supporting this effort. Again, We need to get people off this planet in serious numbers in order to save the human race and to save the earth. Okay, so that I'll make a video about, I have a video about that. I'll make a better video about that. Thank you very much.